So last time I explained that the Hartshorne-Rao module might be very helpful to construct a space curve, and I'm going to construction of a curve of genus G equal, I think I choose 12, and the degree should be 13. So, and to motivate this a little bit, so in P3. So just to get H0 and H1 right, so we get sort of H0 of C of 1 minus H1 OC of 1. This should be 13 plus 1 minus 12, which is 2. Right? So this should be 4 and this should be 2. Right? And any general curve will have such a linear system, because 2 times 4, H0 times H1 is less than G. In a certain sense, it would be much more reasonable to construct, to choose this CS3 than we have it have a different degree. Then we should have a smaller degree. Because then we would set up a curve of finite learning models. But this also gives, of course, if I do go to the Brunner dual system, I produce a curve with a G18. So C, okay, so this is a go. And there's no reason why this shouldn't work. So, and the idea I want to construct this curve was via an OE-Northcott complex. I have OCO. Then here I will take a vector bundle F plus possible a direct sum of line bundles, and here L2. So this here will be a vector bundle version of the Hilbert-Birch. So this here is a Hilbert-Birch matrix. F will be a vector bundle, and H1 star of F should be H1 star of the ideal sheaf, and L1, L2 should be direct sum of line bundles, so they won't have any middle cohomology direct sums of line bundles. So that's the general approach I'm going to take. There's an equivalent approach I could take here, direct sum of line bundle, and here a bundle G plus a free bundle. That's sort of basically equivalent. I usually like to use this. So the question is, what is F? How do you choose L1 and L2? And how we choose this matrix phi? Once we have this matrix phi, of course, then the minus of phi gives this map by the Hilbert-Birch theorem. So it's sort of okay. So postulation of C. So we have N, we have H0 of OC of N, and we have H, and I have H1 of IC of N, and I have H0 of O P3 of N, and then I have H1 H0 of IC of N, right? So it's a short exact sequence, and it can compute these numbers. So here it's 4 and 4, and of course the curve is non-degenerated, and this is an isomorphism. The next step, I have the degree is 13. So here I will have 13, 2 times 13 plus 1 minus 12 will be the dimension of H0 of OC of n, right? So this is going to be 27 minus 12, this is, I think, is going to be 15, and this here will 3 choose 2 9. This is going to be 10. Right? Dimensional. So this was 15 dimensional, 10 dimensional, and now I want to make an assumption which is an open condition. And the open condition which I want to put is that this map between these spaces here has maximal rank for any n. So it's either injective or surjective, or, right, depending. So if it's maximal rank, then of course when we have here 5 and there 0. Next space, we go 1 degree higher, it's 13 larger, so this is going to be 28. And the next number is 4 plus, this is 3 plus 3, choose 3, which is 20. And again here we see an 8, nothing there. And then further degree higher, 13 more is 41. The next binomial coefficient is 35, right? 7 choose 3, 35. So we get a 7 here. And nothing there. And then the next step is, let's see, H choose 3. So here we have 54. And I think this binomial coefficient 3 plus 5 choose 3, 8, 7, 6, 56. And now I will assume maximum rank implies that this will be surjective, and I have 2 in the kernel and so on. Right? So I can work out now.
Here is 2.
There's a 2, there will be, here's a 0, and then there's a 2. So there will be 2 forms of degree 0, 1, 2, 3, 4, 5. So we rely on 2 quintics. All right? Mm-hmm. So I do know the Hilbert function of the Hutchinson-Rout module. So I like M be H1 of I of the H1 of the ideal sheaf, the Hutchinson-Rout module. And this is Hilbert function, well, 5 elements is a finite length module. So Hm of t will be 5t squared plus 8 t cubed plus 7 t to the 4. And if I write this in terms, and then Hm of t times 1 minus t to the 4, a 4 variable, this will give me the Hilbert numerator. This is going to be 5t squared minus 12t cubed plus 4t to the 4 plus 4t to the 5 plus 9t to the 6. I mean, I just multiply this out. There's nothing to it. 16t to the 7 and then plus 6 to the 8. And I deduce from this the expected syzygies. I have 5 generators in degree 2. Then 12 here, 4, 4, 9, 16, 6. So this is the Betti table. This will be the Betti table of M. So of course, in principle, it is a priori possible that these numbers are larger. For example, here could be 1 and this is 5. It's only on the diagonal things are constant, but this is the smallest solution which I have. Right? This is the smallest Betti numbers I could have, since Betti numbers semi-continuous in flat families of modules with constant Hilbert function. It's the safest. The condition on C that the Hartshorne module will have this resolution, Betti table of the resolution, is an open condition. Right? So similar, we can compute beta of SC, of the coordinate ring, and this turns out to be 1, 2, 3, 4, and these two quintics, 9 sextics, 16, 6. And also can compute beta of gamma star of OC of the section module, which will be 1, and then I have these 5 extra generators here. It will be 5 here. It will be 12 there, and then I get a 4 and a 2. And look how nicely these 3 tables fit together. So that is these expected Betti tables, and you see that basically, if I have this table here, so the construction is now given M. And so I've given M, and then I choose F to be the kernel of this map from 12 O minus 3 to 5 O minus 2. So this is a rank 7 vector bundle, right? So this is my F here. The L1, I will choose trivial, 0. So L1 will be 0. And L2 should be these two things. So this should be 4 O minus 3 direct sum 2 O minus 2. And of course I am here, right? I have to choose all of those 4 sections and then 2 of these. So there's a choice. The choice is I have a G2 4. I can choose a 2-dimensional subspace of this 4-dimensional space. That will be the sections, and that's a choice which I have at this point. Once given M, I have a choice of a G24 general point should give me a curve. Okay. So the question is, how do I find the module M? Right? Once I have the module M, then there's an easy choice, and I have to check that it works. That's I can do this by computer, so this will be very harmless. And since I've only chosen open condition, I will know that this will be a dominant family. All right. So, but I wanted to point out more. This 2, 4 plus this 2, 9 is this middle term here. And the end here is, of course, the end there. So it fits very nicely together. So basically what happens is we distribute, in this particular case, the Betti numbers of a Hartz-Rao module and the Betti numbers between the Betti numbers of the ideal sheaf of the section rank and this. I mean, basically every number occurs twice. We have twice a 6, we have twice a 16, twice a 9. We have here we have 4, but we have a 2 and a 2. The 4 occurs twice, the 12 occurs twice, the 5 occurs twice, and the 1s occur also twice. So this is rather nice how this sort of distributes. So the easiest way to specify a module would be to take a presentation matrix, a 5 by 12 presentation matrix, and I might ask what will be if I choose this matrix here, general. So the next step is how to find M. Well, we could try to find the presentation matrix, this 5 by 12 presentation matrix. However, if I choose a general 5 by 12 matrix of linear forms, there will be no syzygies. The Hilbert function, this here had Hilbert function 5, now I erased it, 5, 8, 7. In general will be 5, then 8, and there will be no relation, so this will go down now 3. So if I choose a general 5 by 12 matrix, compute it as a Hilbert function of the co-kernel, it will be 5, 8, and then not 7, but 3. So this matrix has to be special. Of course, I can also choose this matrix here, right? In the dual way, and then resolve it backwards and take the dual complex, right? But again, if I took a 6 by this must be, did I do here something? I must have done something wrong here. I think this better be a 6, otherwise it's not going to work. Right? And I must have made a mistake, yeah. I just, in the computation here before, I made a mistake in taking a difference. Yeah, it was 41 minus 35, and I wrote 7, but it's 6. So the Hilbert function is really that. And if I choose a general one here, it would be 6, 16. So I get a 6, 8 module, but then there will be nothing here, right? So I'm not able to choose this matrix or that matrix randomly. These matrices are special matrices. So instead, I would like to force these 4 syzygies here. So the trick is choose psi a general 12 by 4 matrix of linear forms. So and then the 5 of course should compose to 0 with this, or dually then I have sort of 5s 12s minus 1, and how many things do I get in degree? How many syzygies will be there if this is sort of general, size general? So there will be some syzygies of degree 2, and how many are there? Well, we have here 48, and here we have 4 times 10, which is 40. So this will be at least 8. So the first step is first choose C, a general 12 by 2 matrix. The second step is now to choose a 5-dimensional subspace of this 8-dimensional space and form this 5 by 12 matrix. Right? So I dualize this maybe, right? So now this is then the presentation matrix of, it's going to be the presentation matrix of the Hartshorne-Rao module. So I have 5, 12, and of course by construction I get this 4 here. So I have constructed then a module with Hilbert function 5, 8, 6. Now, of course I don't know this, but I expect that if I take this module there should be nothing in here. There's no reason why there should be something there. So actually, so if I start out with this matrix here, I get the 4 for free. And then the other syzygies, these other 5, 9, 16, 6, they come they come for free. They sort of they're there for numerical reasons, because the Hilbert function here, because I expect here to be 0. Why should that module not have finite lengths? I mean, clearly it wasn't surjective here, at least 2 in the kernel. That was clear from the beginning. Now I have 4 more because I forced this. So I have 6 in the kernel, but why shouldn't I get everything here? Right? I mean, there's no reason that doesn't happen, and it suffices to check that it doesn't happen. So this is n, this gives n. And then, so this is the first choice, and then the third choice is this point in G24, which then gives rise to C. Okay. And that finishes the construction. So this trick to force syzygies seem to work fine if you have only 3 non-negative degrees in the Hartshorne-Rao module. Because, I mean, what could be the nice shape of a Hartshorne-Rao module with only 3 terms? So I'm now finished with this construction. I only have to make this construction explicit in the sense that I have to do one single example and check that my example will lead to a smooth curve. Then I've proved the unirationality of M12, or the Hilbert corresponding Hilbert scheme. So so this works for C with expected Hartshorne-Rao module non-zero in only 3 degrees. If it's non-zero in only 3 degrees, then I will have A, B. Now, depending sort of as a range, I might have a C here, D, E, F, G. That's sort of the hardest case, right? There might be easier cases where C is 0, just depending on these numbers. Then, of course, I can choose basically this matrix most likely arbitrarily. Or if it's here, I can choose this matrix and specify 3 consecutive degrees. And there's no reason why I can't do this general. If such a module exists, such a choice of matrix will give one. Now, if I have this situation here, similar, I mean, of course, I could have sort of, if this is here, then I work with a dual module, with a K-dual module. And that will have sort of in 3 consecutive degrees, because I forced these generators here will have the right number of generators, right? So I basically say that I can, with these p's here, I can force 3 degrees. And maybe I have to start in the inner part, go here and do that. That is it. So they have this shape, or A, B, C, D, E, F, G. That's easier, or right, or A, B, C, and this there. So there's a certain number of shapes which are possible, and if you find in the Macaulay code there's a random space curves. That's a package, M2 package. And it basically works out all the examples where this easy idea works. It will be limited, of course. The Hertzsprung module tend to be in the end larger. And particularly it stopped to work after genus 13. It works for genus 13. And if I take sort of a curve of genus 13, embedded into the degree 13, genus 13, that will work still and produces these curves. So there's a package which produces these curves at random.
Degree 13.
Well, so
genus 13.
Yeah, so it works for. This is the Shanghai. This is degree. So you have degree 11, genus 11. Degree is degree 12, I guess. This is as a Chang-Brown cases, D equal G equals 13. Then there's this, then we have G equals 13. D equals 13. So this is the Chang-Brown space curve which dominates the moduli space, and will work for this example. And then there's also this one for Sanesi, which is degree 12 and genus 12. Mm-hmm. I did a slightly different example. I guess I did. What did I do? I had the example I did was different. It was degree 13, not degree 12, right? So slightly larger degrees of these kind of models are finitely many, and I had a family of models for a given curve because I'm higher Brunet of this. So let me maybe come to an end with what goes wrong in larger degree. So as a corollary of these constructions, corollary of the computation of the construction in computation, Mg is unirational for G equal 11, 12, and 13, right? So that was a reason why Shang and Ran considered this. So Particularly a tempting case for space curves would be degree genus 16, because right, a curve as a genus 16. So we could H0 equal H1 equal to 4. There are finitely many models of this kind. So we could take and try degree 15 and genus 16. And what I would like to finish with is a short discussion what I know about this example and why I can't do it. So the first thing is, by the same computation as before, the Hartz-Rao module M. We have Hilbert function 5, 10, 10, 4. So this is in V2. Under the maximal rank injection. So maxa. And the Belly numbers are going to be 5, 10, nothing here. Here will be 4. And then I think it's 4, 6, 4, 9. Let's see. Where does this make sense? So this will be the Betty numbers. And now, you see, I can try to choose this 5 by 10 matrix. And if I choose a general 5 by 10 matrix, then the Hilbert function will be 5, 10, 10. But the 4 will cancel. The 4 comes that I have here syzygies. On the other hand, if I choose this map here first, then there will be no syzygy, so this will be a very special map. So if again do the decomposition in these tables, you'll find out that this is a resolution of gamma star. This is beta of gamma star OC. And the other one will be 1, and then the remaining stuff 9, 4, 6, 4. This is gamma star of SC. So in this case, there's no extra choice from parsing here. I have to take this piece here, I have to take this map here, and then that is going to give me the curve. So there's no extra choice involved in the Hartz-Rao module, and passing from the Hartz-Rao module to the curve. So the Hartz-Rao module really in this times determines the curve completely. So there's a problem to prove the unirationality of modular space of a curve of genus 16. One possible approach would be to prove that these matrices which can occur, these modules, that they have from a unirational space. And that I don't know how to do. I know that the general curve has these kind of Betty tables. I can construct a reducible example which has this kind of Betty tables. And this module here has interesting geometry. For example, there's a 6 by 4 matrix. So this 6 by 4 matrix gives 20 determinantal points. So this module M, if I put it on top, if I take the M dual, in the module with Hilbert function 1, 10, 10, 5, it will be a quotient of the Hilbert function of a determinantal matrix of 5 by 6, so it will be 5. There's 6 relations, so this will be 10, and then it will be actually 16, 20 will be the Hilbert function. And the kernel will be a module, I think this was 6. It will be a module with Hilbert function 6, and then 15, and then 20. Altogether, so this is 20. So, what I do know, if I take the Hilbert scheme of curves of degree 15 t plus 1 minus 16 on P3, then I have this Hartshorne-Grauer module. This is so basically birational to the Hartshorne-Grauer modules to the space of M's. And from the space of M's, I will map to 20 determinantal points. And what I know is that this map is dominant. So there's nothing special about this matrix. It's a general matrix. This matrix here is a general matrix. But the fibers here don't seem to be rational. So I tried a little bit to work with these 20 determinantal points on this, and you can see that these 20 determinantal points have to lie, need 20 determinantal points to lie on a curve, lie on a 6 by 5 determinantal curve. But so this 6 by 5 comes basically, if I dualize this map, then I get a 5, and 5 and 10. So so basically here I get sort of, you can sort of see in the determinantal curve. But however, it's not that, I mean, it would be easy to produce a 6 by 4 matrix and make it a 6 plus 1 knot, should be not of this type. I should not add simply a column, but I should. But there is a determinantal curve, so which shows up in this picture naturally, and is intrinsic to the curve. I know that these 20 points do not lie on the original curve. I know that this extra determinantal curve doesn't intersect the original curve. So somehow these curves in P3 come together with 20 determinantal points. They're somewhere in space and I have no idea where they really lie. Whether they have some special properties, whether these are points, if I project from that point something particular happens, I have no idea what these 20 points mean. I can choose 20 determinantal points, I can do 20 determinantal curve, 6 by 5 determinantal curve. But what I can't do is to choose them simultaneously to get the points on the curve. So I think this is as far as I would like to explain constructions. If you like, I can give you one more example, which is extremely beautiful, which is the one of Vera. So Vera did the case genus 14.
So genus 14 is also unidirectional?
Yes, Vera, genus 14. It's very beautiful. And it's only one little computation which Vera did, which nobody else did before. I show you that computation. So he works with H to be K minus G1 8. And D minus D, and D moves into G1 8. Why does he do this? Well, if I have sort of 2 minus 7 is equal to 8 plus 1 minus 14, right? So this is correct. So 9, yeah, by both minus 5. So a general curve is finitely many. G1/8. So now Vera embeds the curves with H, which is sort of the linear system K minus D, which ends up in P6. So this is a curve of degree 26 minus 8 is 18. All right, and now he starts to compute the postulation of this curve. So it's 1, 7, and now twice 18 is larger than the canonical, so the next number is 2 times 18 plus 1 minus 14, which is 18 plus 36, 37, 33, is this correct?
Yeah.
On the other hand, 6 plus 2 choose 2 is 8 times 7 by 2. Something is wrong here. I must have done something wrong. The degree is genus 13. 18. 2 times 8. What's wrong here? We are in P6 and
It's 18, right?
The degree is 18.
Yes.
And
So this is 36. This is 23, not this.
this is wrong.
Yeah. This is 23.
23. And this is 28. That's bad. So it follows basically that HC of IC of 2 is greater or equal to 5, right?
Yes.
And I expect equality. So I have these 5 quadrics, and these 5 quadrics intersect presumably in a curve in codimension 5, right? So I have C, I link it with 2 to the 5 quadrics, right? To another curve E. And this had degree 18. So total degree is 32. So this will be of degree 14, right?
Yes.
And what is the genus? Well, we can compute the genus. So the PC minus PE can be computed as follows. So, you know, the canonical on the union is given by the union is a complete intersection. Mm-hmm. So if I take omega of C union E and restrict it to C, I'm going to get omega C. Now assume I have only nodes. If I only intersect in nodes, I will have sort of twisted by C intersected E, right? So, and the same holds for E. So if I take the difference between these two, I'm going to get the difference between the genus if I divide it suitably. So what should I do? I take 1/2, I take C minus E, and multiply this with omega of E, omega of C union E, which is of course O of P6 I5 quadrix, so it's 2 times 5 minus 6, which is, I guess, 4. O of minus 7, which is 3, right? Restricted. So I have here 3H. So, and I can now compute the intersection numbers. So this is 3/2, and the degree 18 minus 14, which is, is this really 3? Yes. So this is 4, so this is going to be 6. So it follows that the genus P of E is going to be 14, genus of P of C minus 6, which is of course also smaller, right? It's smaller. That's the main point. The genus is now 8, right? 14 minus 8. So what we expect under this embedding, that the curve lies on 5 quadrics, that these 5 quadrics intersect in C union another curve, which is a curve of degree 14 and genus 8. Now, is it difficult to find a curve of genus 18 and of degree genus 8 and degree 14? Well, we have this Mukai's theorem. E, a general curve, canonical curve, of genus 8. Then it follows that E can be described as G26 intersected with the P7 inside Plücker space, which is P. Plücker space is 6 just to P14. So G26 has dimension 2 times 4 is 8, codimension 7, so this is a curve. So you prove that any general curve arises as a transversal intersection. Now what I need, however, is a line bundle of degree 14. And I'm going to get this line bundle of D. So I need OE of H, right? I need that in addition. And I'm going to do this as follows. I take omega E, which is of degree 14, and I take 8 and add 4 points and subtract 4 points. If I have the 2 effective divisors of degree 4, if I run through all the effective divisors of degree 4 and take the differences, I have an 8-dimensional family. This is sort of is in pick 14 of C, this will be general, right? It will get a general point in there. So that is actually very nice, because now I'm going to reverse this construction. So I take G to 6, and I choose the points in here. I choose here P1 up to Q4. These are 8 points. Then I take P1 up to Q4 span, which is a P7. And I take C to be the Grassmannian to 6 intersected with this P7. Then of course I have these points on that curve. There will be general point on that curve, and I have sort of constructed so this is E, sorry, this is my curve E. I have this constructed this curve together with points. So it's just right. I mean, this here gives a little bit more. I mean, of course Mukai proved that P14.8 is unidirectional, right? P14.8 over the modular space M8. This is unidirectional. Yeah. So I know this already. Then I go back to this curve, embed it. Turns out it lies on 7 quadric. It lies on more quadric. It's plausible, has smaller degrees, smaller genus. It's sort of plausible that I have lies in more quadrics, will be 7. Then I pick general subspace of 5 quadrics and link back. And that is Mukai's construction. So
Mukai's construction.
And this is Vera's construction. Vera's construction. Mukai's result is sort of course, very different in nature. He uses vector bundles techniques to prove this beautiful result. Right? He proves much more. He precisely which curve has this description. Okay. So. But this was well established, and I think in Vera's construction, really the main point was this computation, which obviously I had difficulties with performing, namely that I have 5 quadrics to compute these 5, right? That was the main point. Once I have the quadrics, 18 plus 14, this is 32, and 18 is larger than half of 32, right? So this is going to be of smaller degree, and of smaller genus. So E should be an easier curve, and easier curve, maybe I understood. So we can go backwards and do this construction.
Okay. So why Chern-Gibran's method is not just effective in this case?
Well, because the Hartz-Grau module has sort of 4 is non-zero in 4 steps. I mean, there will be Hartz-Grau. You can compute the expected Hartz-Grau module, but as in this example here, there will be 4 different degrees where it's non-zero, and I don't know how to construct such a module. The Hartz-Grau module is a difficulty. Everything else is easy, and it's not clear. Right.
So what has been done up to higher genus, and you have a more interesting? Yes.
This is still the record.
I see.
So I worked a bit on Hurwitz schemes. So the curve together with a pencil, and I looked always at the pencil of the curve embedded, like in Vera's case, with K minus D. And then you could ask, I mean, which Hurwitz schemes of, so we have the Hurwitz schemes H and GD, which is sort of C to P1, D to 1, right? Of genus G. Right, this might or may not dominate MG. And so what do we know about these spaces? So I looked at a little bit, this looks a little bit more promising. So you know, so if D is small, for example 2, hyperelliptic curves are universal, trigonal are universal, fourgonal are universal, fivegonal are universal using, this is due to Petrie. Actually, the structure theorem of Boxbaum Eisenbart tells you that, on the corresponding scroll, which you get in the canonical swept out by the G1D, the curve is Pfaffian. So we can choose the Pfaffian matrix generically and get that. 6, D equals 6 is a case where we, my student Florian Geist proved something like that. Sort of they are universal up to the case genus something in the 30s, and then that sort of gaps. The last case he could do was 45, the one before was 40. So then it sort of his method stops. He uses liaison in P1 cross P2, so he uses curves in P1 cross P2. Then you have Mukai's result, which basically says that if G is less than or equal to 9, then it will be universal for any D. Yes. So, and then, well, we have only outside that range, so D less than or equal to 5 or G less than or equal to 9 are all unirational. All HGD are unirational. And outside, finitely many further cases are known, and I don't quite know whether I should expect that there are infinitely many further cases or only finitely many cases. I could imagine that Vera's example actually is an extremal example, so I worked a little bit on this without right. So I think I should come to an end.
Thank you very much.